Hi, this is Lab 2 Projectile Motion. So the purpose of this lab is to observe real-world motion of an object in projectile motion and compare it with theoretical models of the same projectile motion in two instances with one only gravitational force acting on it and two with gravitational and drag forces acting on the object. The lab will use this comparison to examine the influence of different forces on objects in projectile motion. So for this experiment, the system is the whiteboard eraser and the surroundings is all other objects in the room where the experiment took place, including the table, ruler, and etc. The fundamental concepts used in this lab include position update formula, the momentum principle, which leads to the velocity update formula, gravitational force, and drag forces. And in this lab, by using essential equations, we produce theoretical models for the trajectory of an object in projectile motion. And in this lab, we're comparing them to the object's actual motion. So both motions allow us to examine the influence of gravitational and drag forces on an object's motion as concepts and real-life forces. And this is a visualization of gravitational and drag forces acting on objects during projectile motion. In the experiment, the procedure was to record a video of an object traveling in projectile motion, importing the video onto Tracker to track the ball's position at set time intervals according to X and Y axes defined in the software, which I defined, creating a computational model of the ball's position according to these same axes in the Tracker software, which serve as the ideal motion of the ball in ideal conditions. And we produced two results, with one showing the ideal motion of the ball with no forces except gravitational force from the Earth acting on the object, and the other being the ideal motion of the ball, considering both the gravitational force of the Earth and drag force by air resistance. And then finally, we're importing the data onto Google Sheets to create a graph modeling the actual motion of the ideal and predicted motion for analysis and comparison. This is the tracker video. Very good. Sorry. Okay, anyway, so we come up with the initial conditions and parameters from the first two, the first two positions from the tracker video, and so that helps us determine the time between each position, initial velocity, drag force, and its proportionality constant for the drag force. And so the code for no drag is indicated by the b being equal to 0. And for the code, it helps us define system properties and initial conditions to create ideal model of motion based on actual conditions of the experiment, to create an ideal model of motion for prediction and visualization using the momentum principle and fundamental concepts. Also, the ballpoint M equals 0.038 kilograms is actually the real weight of the ball, of the object, which we weighed with a scale in the lab. And it's the same for the code with drag, except we change the proportionality constant to 0.1746 newtons per meter squared per second squared. So this is the model for when only gravity acts on it, and this is with drag forces included. So when we plot them all together, we see that position increases until a similar increment between 0 and 0.2 seconds, but there are a lot of differences. So the predicted motion with no drag has much more height and starts falling later than the red and yellow. The red and yellow reach max height within 0 and 0.2 seconds, and blue reaches max height within 0.2 and 0.4 seconds a little later. And the predicted and actual with drag forces are very similar in the interval 0 to 0.2 seconds, then the actual motion falls much less than the predicted motion, which suggests the value of drag forces isn't equal to the weight of the object, and that there are other unknown forces acting on the object that influences its motion. A lot of the error in the tracker software is human error, so like scaling, calibration, marking the center of the object, and also the assumptions aren't true because we assume that there are only two forces acting on the system, which are drag and gravity. But in reality, we can't perfectly measure the V proportionality constant for drag because one, we based it off of an estimate of V, which isn't instantaneous, and two, by the nature of the experiment, it wasn't taken in a closed and completely controlled environment. There may be unknown forces acting on the object during projectile motion, aside of gravity and drag forces, which makes the sum of forces F grav equals F drag, which we use to solve for B, not true. So both models predicted a terminal velocity, and then since Phi and P, yeah, Phi are equal for both instances, we know that as a component of VI sine theta will always equate to a lesser value than that of VI since it's a component. So if VI sine theta is less than VI, the total time it takes to reach the ground will be longer when thrown directly upward instead of being thrown with a ball with both a horizontal and vertical component.